Welcome back to machine learning. Today's video is going to cover decision trees. In this video, we'll cover what a decision tree is and how to generate one. Decision trees are a machine learning model. We'll learn about a lot of models in this class, and this is going to be the first one and one of the more simplistic ones. Let's start with an example. Here we have 4 samples and we have 2 features, sunny and greater than 90 degrees. And then we have our label outside. The problem here is that we know whether or not it's sunny outside, and we know whether or not it's greater than 90 degrees, and we're trying to predict if we should go outside. We have 4 samples, and I've labeled them 1, 2, 3, and 4, so we can refer to them easily. But the sample number is not a feature. We can think about this as being 4 different days, and on the 5th day, I'm trying to predict whether or not I want to go outside. We have a binary problem here. That means that the label that we're trying to predict outside has binary values, 0 or 1, or in this case, no or yes. We start by building a tree. We start with the root node by asking about one of the features. Let's start with sunny. So if we say sunny and then we have 2 branches, you can either have it be sunny, yes, or have it not be sunny, no. The data splits on these 2 branches. If it's not sunny outside, we have samples 3 and 4. And if it is sunny outside, we have samples 1 and 2. Now, typically when you're building the decision tree, you keep track of all this information, specifically the samples that are in your subset, depending on which way you branched. But we normally don't write these things down. I'm writing them down here so you can see them, but you don't want to do that all the time, and that's not what the final tree is going to look like, as you'll see in a minute. But this is just while we're working through the problem, we'll keep track of what samples we're looking at. What if we stopped building the tree right here? How would we do on the training data? The training data is this data that's available to us right here. And we're using it to build this tree. Well, let's look. If we see samples 3 and 4, they have a label of no, so I shouldn't go outside. And samples 1 and 2 have a label of no and yes, respectively. So how well could we predict whether or not we should go outside? Well, we could say no if it's not sunny, because on the left-hand side, it's always no. We would get 2 out of 2 correct if we did that. And we could say yes on the right-hand side, so if it's sunny, then we would get 1 out of 2 correct. Overall, we would have an accuracy of 75% on the training set. But we could also say no on the right side and get 75% on the training set, and that's not so great. Why do we even have to build a tree if we can just say no and get 75% on the training set? We have another feature that we can look at. Let's ask another question first. Let's look at the left side of the tree. We can see that we have 2 samples on the left side. And both of them have a label of no for outside. We don't need to ask another question if both of these have the label of no, because we can just say no and be done with it, and we'll get 100% on that side of the tree. Let's move on to the other side. On the other side, we have a label of yes and a label of no, so we're getting 50% accuracy on that side of the tree. If we ask a question about the other feature, which is greater than 90 degrees, maybe we can do better than 75% on the training data. We ask this question and we have no and yes as the answer. So we have no here and we have yes here as the answer to that question. On the no side, we have the sample 2, and on the yes side, we have the sample 1. It turns out on the left side, sample 2 has a label of yes, and on the right side, sample 1 has a label of no. So on the left side, we can say yes, and on the right side, we can say no. And now we're getting 100% on the training set. This is what our final tree would look like. It simply has questions about the features, And then at the leaves, it's a decision, a no or a yes, because we're dealing with a binary problem. These are the leaves. What's the point? Well, the point is that we save this model, which is just a tree, and then we can take new samples of data. So on day 5, we take the information for day 5, including whether or not it was sunny and whether or not it was greater than 90 degrees, and then we make a prediction about whether or not we should go outside or whether or not we did go outside. If we take this sample 5 and we see it's not sunny, that means we go to the left immediately and we say no. So it's not sunny, we come down here and we say no. So if day 5 hadn't happened, our model would say don't go outside if these are the conditions. And if day 5 had already happened, it would have said, okay, you shouldn't have gone outside. I don't know what you did, but you should not have gone outside. It's just making a prediction based on what it has learned, and it only learned from days 1 through 4. We can see that sample 5 exactly matches sample 3. And so it makes sense that the prediction would be the same as sample 3. This begs the question, could we have created the decision tree differently? And the answer is yes, absolutely. I arbitrarily chose to start with sunny, but we could start with 90 degrees. If we start with 90 degrees, no is on the left, yes is on the right, and we get 50% accuracy on the left and 100% accuracy on the right. How well would we predict going outside on the training data? Turns out we'd be at 75% again if we start with 90 degrees. We have samples 2 and 4 and samples 1 and 3 separated. On the right-hand side, for samples 1 and 3, the labels are both no, so we can just say no and move on. On the left-hand side, we're getting 50% accuracy, so we should ask another question. The only other feature we can ask a question about would be sunny. With sunny, we now only have one sample on each side. On the left side, we have sample 4, and on the right side, we have sample 2. With this, we can predict no on the left side and yes on the right side, and we would get 100% accuracy on the training set. This is what our final tree would look like if we started with 90 degrees instead of with sunny. Again, the sample information is not actually saved in the tree because we don't have that data at test time. We just have the tree, which has all the nodes and branches and the leaves. The leaves are our final decisions. The point is, we could take a new sample like this one, which has no for sunny and yes for 90 degrees, and run it through the tree and make a prediction. So on day 5, should I go outside? Well, it's not sunny and it's greater than 90 degrees. If it's greater than 90 degrees, we go to the right and we say, no, it's too hot. Don't go outside. We got the same result when we used the other tree where we started with sunny. There are many different ways to build a tree, and we'll learn a specific way using entropy and information gain a little bit later in this video. One thing to note is that in this particular training set, we have every possible combination of features. We have yes, 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 no, no, yes, and no, no. There's nothing we've not seen before, and there's no samples that contradict each other. We could have a sample, let's say no, no, and the outside label is yes in that situation, and we would never be able to get 100% accuracy on the training data because we have a sample here, no, 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 and no, no, yes. And with only 2 features, we can't predict 2 different things. So we have a contradiction, and we would never be able to get 100% on the training data if it was set up like this. We use a greedy algorithm to build the decision tree. That's what we were doing before. We decided to split using accuracy, but it was kind of random, and our first point gave us 75%, and we could have just said no all the time and gotten 75%. So there's got to be a better way to split. And indeed there is. We're going to use what's called entropy and information gain. We're going to use the definition of entropy that's a part of the field of information retrieval. Entropy is a very complicated concept, and almost every field has a different definition of it. In this class, you can think of it as a notion of surprise. The more information that's contained in a set of data, the more surprise you have. If I come home every day and my dog is very excited to see me, and I come home today and the dog is still very excited to see me, nothing is new. Nothing unexpected happened. If I come home the next day and my dog is not excited, doesn't come to the door, seems kind of lethargic, that's a cause for concern. Suddenly there's new information, and something surprising gives us new information. You can think about entropy in the same way. Entropy uses a capital H right here. In this class, we're going to use kind of a weird notation so we can denote all the different splits properly. That's this parentheses S. We can use a notation for that gets long but is very informative. So here we have H with S inside the parentheses. This is the entropy of the set S. The entropy of a set is simply the sum of the probability of each class multiplied by the log of the probability of the class. Little c is going to be the class that we're looking at, and big C is going to be the set of classes. What are the classes? No and yes, or 0 and 1. Binary, remember? Those are the labels, no and yes. And so all this is the sum of the negative probability of no times the log of the probability of no minus the probability of yes times the log of the probability of yes. It's a lot. We're really going to take it slow and go through each part of this. First, it's probably been a long time since you've had to deal with logs. I know I have to refresh my memory basically every time I deal with them, so don't worry about that at all. Remember that a log of a number x is y, where y is the exponent of the base of the log. What we have here is the base 2 log of x. This is converted to 2 to the y equals x, and then you need to solve for y. That's our answer. I know it's a lot. Let's look at an example. Log base 2 of 4. If we have 2 to the y equals 4, y must be 2. So log base 2 of 4 is 2. Another example. 2 to the what equals 1/2. Y must be -1. So the log base 2 of 1/2 is -1. Don't worry too much about it. I just want to make sure you have an understanding of what it is so you don't panic. There's nothing to panic about here. Let's look at some examples of entropy in this situation so we have a better sense of what's actually going on here. Here I have visualized the log function so you can see what it looks like. We have a set of sample data. You can see here we don't have any features because entropy doesn't care about features. We only care about the label. This is important. I'll repeat it. We don't need feature values to calculate entropy, just labels. Let's pretend like there's a couple features that we just can't see, and we have 4 samples and 4 outputs. We have 4 labels, and all of them have a label of no. Let's calculate entropy. Entropy is going to be the negative probability of no times the log of the probability of no. What's the probability of no in this case? Well, it's 1, because 100% of the samples have a label of no. So we have -1 times log of 1 for the no label. And now we do the yes label. We need the probability of yes, which is 0, because there are 0 samples in the dataset with a label of yes. So for the label yes, we have 0 times log of 0. What does this reduce to? It reduces to -1 times 0 plus 0 times -infinity. 0 times -infinity is going to be 0. The 0 always wins. Entropy in this example is 0. What does that mean to me? Or more importantly, to you? That means there's nothing interesting here, nothing surprising. There's no information. That shouldn't be surprising to you, right? Because all we see here are no's. So it's kind of like every day coming home and your dog is excited. It's the same thing over and over again. Not bad, just not surprising. Now, if we look at the opposite case where the label is always yes, we get the exact same result. It's still unsurprising, right? You can see the probability of no is here, the probability of yes is here, so they just swapped. Now for a more interesting case, If we have 4 samples, 2 of which have a label of yes and 2 of which have a label of no, we get a more interesting value for entropy. What's our probability of no? Well, the probability of no is 1/2 here because in 2 out of 4 samples, the label is no. What's our probability of yes? It's also 2 out of 4, which is 1/2 again. Then our entropy becomes negative 1/2 log 1/2 minus 1/2 log 1/2. So what is that? It's 1. Remember that the log of 1/2 is negative 1. We reduce all that and we get an entropy of 1. This is the largest entropy value we can get. So this is the most exciting entropy because everything is random. Let's look at one final example. If we have 3 yes labels and 1 no label, then our probability of no is 1/4 and our probability of yes is 3/4. These probabilities make our entropy 0.811. So it's less surprising than the last example, but much more surprising than if all the labels were the same. Now that we know what entropy is, we can talk about information gain. Information gain is what we're using to split our decision tree. Information gain is simply the entropy of the full set minus the probability that a sample ended up on a particular side of the split times the probability of that split. It sounds complicated, but trust me, it's not. I think it's best to go through an example first. Let's look at our tree that we built when we were dealing with this set of data. Remember, we were trying to decide if we wanted to go outside and our features were sunny and greater than 90 degrees. With our first feature split being on sunny, we have 3 and 4 on the left side and 1 and 2 on the right side. Remember, we said no on the left and yes on the right. Let's think about what's happening here in terms of entropy and information gain. First, we need to calculate the entropy of the whole set. We do that by calculating the probability of the label no, which is 3 out of 4. And then the probability of the label yes, which is 1 out of 4. Then we calculate entropy using these probabilities, 3 out of 4, 1 out of 4, and we get 0.88. That's the entropy of the whole set. We split on sunny, so now we have the points 3 and 4 on the left and the points 1 and 2 on the right. We want to see if we gained any information by splitting in this way, so we need to calculate the entropy of the left side and the entropy of the right side. The entropy when sunny equals no is going to be this equation on the left. This is the reason we use these parentheses, because we start adding conditions inside of them, and these conditions create these subsets. So the condition sunny equals no creates the subset of samples 3 and 4, and the entropy of this subset is 0. Because both samples have a label of no. Make sure to calculate that out on your own and make sure you get 0. Now, on the right-hand side, we have the subset 1 and 2. The entropy on that side is 1 because it's 50-50. Make sure you calculate that on your own and you also get 1. Now that I have the entropy of both of my sides after my split on sunny, I can calculate information gain. Remember that information gain is the entropy of the whole set minus the probability that a particular sample ended up on one side of the split times the entropy of the side of the split plus the probability that the sample winds up on the other side of the split times the entropy of that side of the split. On the left side, what's the probability that a sample ended up on the left side? Well, there's 2 samples on the left side of the split, and there's 4 samples in total. So that's 2 out of 4, 0.5 or 1/2. Similarly, on the right-hand side, we ended up with 2 samples out of 4. So that's a 1/2 as well. We calculate this out and we get 0.311 as the information gained. What do we want? Well, we want both sides of the split to have an entropy of 0. If both sides of the split have an entropy of 0, then our information gain will be very high. Remember that when we are using accuracy, we split here. And it was no better than saying no all the time. Information gain works a little bit differently, and it will actually help us build a better tree. Our information gain was not the same as the entropy when we started. That means that we still have things to learn and we can keep going. This brings us to the greedy algorithm that we're going to use to build the tree. It has roughly 4 steps. Although you don't need to remember them or write them down in this particular order, this is the general order. First, you want to calculate the entropy of the entire training set. Second, we want to split the training data using each feature and calculate the information gain for each split. Third, we want to choose to split on the feature that gives the best information gain, best being maximum. 4, we want to repeat these steps 2 through 4 on each subset until the best information gain is 0. If the best information gain is 0, that means we really can't do anything else or we've run out of features. This is a recursive process. It's probably been a little while since you've covered binary trees or done anything with them, but you may remember that binary trees are built with a recursive process. Let's run through an example now so we can understand how it works. We're going to use this data set for the rest of this video. This data set consists of 10 samples of different TV shows. There are many features, including if the show is less than 40 minutes long, if the show is a comedy, if the show has a female lead, and if the show is political. The label is going to be whether or not I like the show. You can think about this data as a very small subset of some of the data that Netflix has. Netflix is trying to predict what you will like next and what you are going to watch next. So it uses your previous watch history and possibly your ratings to make these predictions. Let's start with our greedy algorithm. First, we need to calculate entropy for the entire training set. I highlighted all of the yes labels in green throughout so that we have a better way to visualize how many samples are yes and how many samples are no. Here we have 4 samples with a yes label and 6 samples with a no label. We calculate entropy like so at the bottom of the screen. We get 0.97. So not quite random, but pretty close. We want to split the training data using each feature and calculate the information gain for each split. If we split on the feature less than 40 minutes, which is going to be all of these blue samples, we see that if we look at only the samples where less than 40 is no, there's only one of those that is labeled as yes. We will get 4 out of 5 correct if we just say no. So the probability of no is 4 out of 5, and the probability of yes is 1 out of 5. That means our entropy on this side is going to be 0.72. Now let's look at the right side. If the show is less than 40 minutes and we have 3 out of 5 labeled as yes and 2 out of 5 labeled as no. Our entropy ends up being 0.97. What is the information gained if we split this way? Remember that entropy on the left side is 0.72 and entropy on the right side is 0.97. The entropy for the entire set is 0.97. So we're going to subtract the proportion of samples on the left side times the entropy of the left side with the proportion of the samples on the right side times the entropy of the right side. There are 5 samples on the left side and 5 samples on the right side, and there were a total of 10 samples. So we have the entropy of the whole set here. We have the proportion on the left side times the entropy of the left side, the proportion of the right side times the entropy of the right side, all subtracted from the original entropy. And we get 0.12 as the information gained for this split. Now we move on to the next feature, which is comedy. The samples shown in blue have a feature value of yes for comedy. If we look at the samples with a value of no for comedy, we see that there's only 1 out of 6 that's labeled with yes, and the rest are labeled with no. We calculate entropy on this set, and we see that it's 0.65. On the right side, when comedy has a value of yes, we have 4 samples, 3 of which have a label of yes. The entropy for this side is 0.8. Now we need to calculate information gain. We know we have 6 samples on the left and 4 samples on the right. Information gain is calculated like this, and we get the value 0.25. Moving on to the next feature, which is female lead. Samples in blue have a value of yes for female lead. If we look at the samples with a value of no first, we see that all of them have a label of no, and this gives us an entropy of 0. Things are looking good. On the right side, when female lead equals yes, we see that 4 out of 7 samples have a label of yes, and 3 out of 7 have a label of no. This gives us a pretty high entropy of 0.98. Calculating information gain, we know that there are 3 samples on the left side and 7 samples on the right. The information gain is for this split is 0.28. This is the highest one we have seen so far. Our final feature, political, has 5 samples with a value of yes and 5 samples with a value of no. If we look at the samples with a value of no first, we see that there are 3 samples labeled with no and 2 samples labeled with yes. This gives us an entropy value of 0.97. Now, if we look at the samples with a value of yes for political, we have 2 labeled with yes and 3 labeled with no. This gives us an entropy value of 0.97. We end up saying no on both sides, which doesn't look good. We know that there are 5 out of 10 samples on the left side and 5 out of 10 samples on the right side. We calculate information gain and we see that it makes absolutely no sense to split on the feature political right now. It would do just as well if we just said no from the beginning and didn't make a tree. Let's look at our options. We finished splitting the data on each feature, and now we need to choose the best feature to split on. Looking at all the features and their associated information gains, which one looks the best? Female lead looks the best, and that's what we should split on. It has the highest information gain, so we'll start with that. If we stopped right now, how would our model do? The model we picked would actually get 70% accuracy based on the split on female lead. If we were using accuracy to build our tree, we would start with comedy, not female lead. Now on to step 4 of the algorithm, which is just to repeat this process down the tree. From here on out, we're going to be looking at subsets of the data when calculating information gain. This is important because the first term in information gain is the entropy of the full set. Since we've split the data based on a feature, namely female lead, we no longer have access to the full data set on either side of the tree. So instead of entropy on the full set, we're interested in entropy of the subset. Let's calculate those first. Looking at the left side of female lead, that is, when female lead equals no, in that case, we don't seem to like any of those TV shows. The entropy here is 0. This means that it is entirely predictable, and so we predict no on this side. Now let's look at the right side of the tree, when female lead equals yes. In this case, we have 4 out of 7 labels of yes and 3 out of 7 no's. This gives us an entropy of 0.98. Why are we calculating this again? Because when we start working with information gain as we continue to split, we don't really care about the entropy of the whole set anymore, because there's those 3 samples on the left that we have nothing to do with anymore. Our new entropy that we're going to be using at the beginning of the information gain equation is going to be this one, the one where we're dealing only with the subset of the data where female lead equals yes. We're all done on the left side, but we can split on the right side. So we have to cycle through the features again. Let's start with less than 40 minutes. The samples that are blue have a yes value for less than 40 minutes. If less than 40 minutes equals no, we have 1 sample that has a label of yes and 2 samples that have a label of no. The entropy here is going to be 0.91. The notation is starting to change a little bit. As you can see on the left side of the equation, we have the entropy of female lead equals yes and less than 40 minutes equals no, because we're dealing with the subset of female lead equals yes from the start. Then we're including, right now, less than 40 minutes. When less than 40 minutes equals yes, we have an entropy of 0.81 because we have 3 samples with yes and 1 sample labeled as no. The information gain for this particular split is going to be the entropy of female lead equals yes minus all of this stuff. So it looks like a lot, but let's think about it. When female lead equals yes, there are 7 samples total. When female lead equals yes and less than 40 minutes equals no, we have 3 samples. And when less than 40 minutes equals yes, we have 4 samples. So we calculate entropy like this, and the information gain is going to be 0.12. Make sure that you calculate this on your own and you're getting the same numbers. It's very important that you understand this process. I'm going to use a little shorthand here so we don't run out of room. So S sub F equals Y is the subset of the full set where female lead equals yes. Now let's split on something else. Let's try comedy. For comedy, we only have 3 samples that have a value of yes, and 4 samples with a value of no for comedy. For comedy equals no, we have 4 samples. One is labeled with yes, and the rest are labeled with no. This gives us an entropy of 0.81. When comedy equals yes, we have 3 samples, all of which are labeled yes. This gives us an entropy of 0. Calculating information gain, we get 0.52, which is very large. This is looking good. We still have to check the final feature, political. Why do we not check female lead again? It doesn't make sense to do that. We can ask again about female lead, but we'll just continue down the right side because female lead already equals yes. Does it make sense to ask another question about it? No. In fact, we would find that our information gained would be 0 if we did that. If we ask about political instead, there are 4 samples with a value of yes and 3 samples with a value of no for political. If we look at political equals no, we have 2 samples with a label of yes and 1 sample with a label of no. This gives an entropy of 0.9. Now look at political equals yes. We have 2 samples with a label of yes and 2 samples with a label of no. This gives us an entropy value of 1. Calculating information gain, we get a very low value of 0.03. That's because entropy was 1 on the right side and 0.9 on the left side. Pretty high values. These are our 3 options. We choose the one with the highest information gain, which is going to be the one in the middle with comedy at the second level. Now that we've looked at this and decided that comedy is the best one to go with, we want to see where we're at. If comedy equals yes, it turns out that we get all of them right if we have the model predict yes. Our entropy is 0 on this subset, and so we're done here. Moving on to the other side, we have an entropy of 0.81 when female lead equals yes and comedy equals no. Still pretty high, so we can keep improving. Again, we cycle through the features starting with less than 40 minutes. Only one of our 4 samples has a value of yes for less than 40 minutes. When less than 40 minutes equals no, we have 2 out of 3 samples with a label of no and 1 sample with a label of yes. This gives an entropy of 0.91. When less than 40 minutes equals yes, we have 1 sample and it is labeled with no. The entropy here is 0, but this looks bad because we're predicting no on both leaves, so there's no point in splitting. Calculating information gain, we get 0.12. Remember this shorthand notation where we had S sub F equals Y for female lead equals yes? Now we have this C here for comedy equals no. The information gain is pretty low, but it isn't 0 even though we're predicting no on both sides. Because on one side we are able to get 100% of the samples correct, just the one sample, but still. This is an instance where we can see the difference between using accuracy and using information gain. With accuracy, we would have just stopped because it makes no sense to split and say no on both sides. Moving on to the next feature, political. Political has 2 samples with a value of yes and 2 samples with a value of no. When political equals no, we see that it's random. We see that there's one that has a sample with a label of no and one that has a label with yes, so the entropy is 1. When political is yes, we have 2 samples, both of which have a label of no. The entropy of this subset is 0. Calculating information gain, we get 0.31. Looking at our 2 options for feature splits at this point, we choose to split on political because it has the highest information gain. Remember that when political equals yes, we have 2 samples, both of which are labeled no. We can have the model predict no here and be done. On the other side, when political equals no, we have an entropy of 1. We only have 1 feature left to split on, and that's less than 40 minutes. So we split on that. Only 1 sample has a value of yes for less than 40 minutes. When less than 40 minutes equals no, there's 1 sample and it's labeled with yes, so we have an entropy of 0. When less than 40 minutes equals yes, there's 1 sample and it's labeled no, so we have an entropy of 0 here as well. Calculating information gain, we get 1, which is the maximum we could get. This means that everything has been perfectly classified and we can stop on this branch. This is our final tree. We ask about female lead, then we ask about comedy, then about political, and finally about less than 40 minutes. Why do we build this tree? So that Netflix can recommend new TV shows. So, if we have Brooklyn Nine-Nine, a new TV show, we know that it's less than 40 minutes, a comedy, the lead is male, and it is not political. We can use our model to predict whether or not we will like the show. We go to the left from the root because it's a male lead, and we don't like it. Next show, Younger, which is less than 40 minutes, a comedy, has a female lead, and is not political. So we go to the right at the root, and then again to the right on comedy, and we predict yes. Here is the greedy algorithm again. Let's focus on step 4. It says that we repeat this algorithm until the best information gain is 0. But we stopped after the information gain was 1 on the last example. I was being lazy there. What you would actually do is run through all the features again, and you would see that splitting on any of them would give you an information gain of 0. And so you would know you were done. Because in practice, you always run through all the features each time, even if you've already split on them. Because it's just a for loop, and the for loop doesn't check to see if you've already split on a feature. Think about this and make sure you understand it. Decision trees are a model and the algorithm is greedy. The algorithm is what creates the decision tree. The model is the binary tree and the algorithm is a greedy one, based on entropy and information gain. That's it for decision trees. The next topic will be limits of learning.